So let's start with the essential ideas of chemistry. So we're going to look at this page right here, and it says by the end of this module, you will be able to outline the historical development of chemistry, provide examples of the importance of chemistry in everyday life, describe the scientific method, differentiate among hypotheses, theories, and laws, provide examples illustrating microscopic, microscopic, and the symbolic domains. So, cool thing to do is when you read a textbook, especially an academic textbook, is to just skim across it just like once, so you can see what's going on here, and you can kind of see we got the picture of everyone doing all their what I guess formerly would be called alchemy, but this is like baking and all kinds of stuff, baking and churning, and I don't really know what all they're doing, but let's just have a closer look. Let's open a new tab. We can get a bigger image of it here. Excuse me, I have to cough really quickly. But yeah, we have all of our people doing things. This is like very medieval. So scrolling down, we see chemistry, the central science, and then right here we have chemistry at the center of everything. Like literally everything you do. So you have geology, earth sciences, agriculture, food science, biology, medicine, biochemistry, molecular science, toxicology, chemical physics, nanoscience, nanotechnology, computer science, even computer science. All of it can be traced right back to chemistry. Scientific method, you've probably heard this term before. This right here, the scientific method, is the way of ruling out everything and reducing it down to its simplest logic. And right here we can see the scientific method in action. And then the domains of chemistry, we'll get to that in a second. Again, the macroscopic and the microscopic domain, the symbolic domain, and all of that jazz here. So let's go back to the top and we will examine this whole thing thoroughly. So throughout human history, people have tried to convert matter into more useful forms. In the past, we may have called that alchemy. Today, some people want to call that other things like witchcraft, but it's not even magic, it's just science. Our Stone Age ancestors chipped pieces of flint into useful tools and carved wood into statues and toys. Some people still do that. These endeavors involved changing the shape of a substance without changing the substance itself. But as our knowledge increased, humans began to change the composition of the substance as well. Clay was converted into pottery. Hides were converted to make garments. Copper ores were transformed into copper tools and weapons, and grain made into bread. Humans began to practice chemistry when they learned to control fire and use it to cook, make pottery, and smelt metals. Subsequently, they began to separate and use specific components of matter. A variety of drugs such as aloe, myrrh, and opium were isolated from plants. Dyes such as indigo and Tyrian purple were extracted from plant and animal matter. Metals were combined to form alloys. For example, copper and tin were mixed together to make bronze, and more elaborate smelting techniques produced iron. Alkalis were extracted from ashes, and soaps were prepared by combining these alkalis with fats. Fun fact about soap, I don't know if you knew that. Soap is very ugly when you first get it. Like before it ever is refined and made to look decent before it comes to the shelf. It's actually just fatty stuff that's horribly looking. You just look it up. Okay, alcohol was produced by fermentation and purified by distillation. Also, that's a very common thing to know there. I mean, not a common thing to know, but a good thing to know. Attempts to understand the behavior of matter extend back to more than 25,000 years. 2,500 years. As early as the 6th century BC, Greek philosophers discussed a system in which water was the basis of all things. Aristotle believed there to be 4 elements: earth, water, and fire. Earth, water, air, and fire. You may have heard of the Greek postulate that matter. Well, there we go. The postulate that matter consists of 4 elements: earth, air, fire, and water. Subsequently, an amalgamation of chemical technologies and philosophical speculations was spread from Egypt, China, and the Eastern Mediterranean by alchemists, who endeavored to transform base metals such as lead into noble metals like gold, to create elixirs to cure disease and extend life. That's all of this right here. This is figure 1.2. This portrayal shows an alchemist workshop circa 1580. Although alchemy made some useful contributions to how to manipulate matter, it was not scientific by modern standards. And we will see that in just a minute. From alchemy came the historical progressions that led to modern chemistry, the isolation of drugs from natural sources, metallurgy, and the dye industry. Today, chemistry continues to deepen our understanding and improve our ability to harness and control the behavior of matter. Chemistry, the central science. Chemistry is sometimes referred to as the central science due to its interconnectedness with a vast array of STEM disciplines. STEM stands for areas in study of the science, technology, engineering, and mathematical fields. Chemistry and the language of chemists play vital roles in biology, medicine, materials sciences, forensics, environmental science, and many other fields. We'll see that in a minute. That's all of this actually right here that we were just getting at a minute ago. The basic principles of physics are essential for understanding many of the aspects of chemistry, and there are extensive overlap between many subdisciplines within the two fields, such as chemical physics and nuclear chemistry. Mathematics, computer science, and information theory provide important tools to help us calculate, interpret, describe, and generally make sense of the chemical world. Biology and chemistry converge into biochemistry, which is crucial to understanding the many complex factors and processes that keep living organisms such as us alive. Chemical engineering, materials science, and nanotechnology combine chemical principles and empirical findings to produce useful substances, ranging from gasoline to fabrics to electronics, agriculture, food science, veterinary science, and brewing and winemaking to help provide sustenance in the form of food and drink to the world's population. Medicine, pharmacology, biotechnology, and botany identify and produce substances that help keep us healthy. Environmental science, geology, oceanography, and atmospheric science incorporate many chemical ideas to help us better understand and protect our physical world. Chemical sciences are used to help understand the universe in astronomy and cosmology. Basically, chemistry is everything that exists. Basically, every science that exists can be tracked back to chemistry. And some you may feel like you're taking some extra leaps of faith with, but in reality, it's all chemical. Everything is chemical. That's why chemistry is so fascinating. What are some changes in matter that are essential to daily life? Well, there you go. There's a question for you in the comments. Go ahead and try and answer that one if you can. But let's see. Digesting and assimilating food, synthesizing polymers that are used to make clothing, containers, cookware, and credit cards, and refining crude oil into gasoline and other products are just a few examples. As you proceed through this course, you will discover many different examples of changes in the composition and structure of matter. How to classify these changes and how they occurred, their causes, the changes in energy that accompany them, and the principles and laws involved. As you learn these things, you will be learning chemistry, the study of composition, properties, and interactions of matter. The practice of chemistry is not limited to chemistry books or laboratories. It happens whenever someone is involved in changes in matter or that sentence is a bit strange. It happens whenever someone is involved in changes of matter or in conditions that may lead to such changes. That sounds like you're trying to say someone is going to change their chemical matter, but I guess technically that's not even technically, literally that's true, because if you're eating food, you're changing the food inside of you to more useful forms of chemistry, or chemical matter, I guess. The scientific method. Here's the fun one. Okay, so we need to actually go through this. Scientific method, that's the thing that keeps everything working. So we want to stay logical when we look at this. We don't want to overthink things. We don't want to underthink them either. So let's figure out what the scientific method is. Chemistry is a science based on observation and experimentation. Doing chemistry involves attempting to answer questions and explain observations in terms of the laws and theories of chemistry, using procedures that are accepted by the scientific community. So you may have heard of the term scientific consensus. That's one thing that sometimes things can go out, like way out there, but once you have a consensus, I'm not actually sure how you spell that. I know how to spell it, but as soon as I try and write it, it's going to look weird. But yeah, scientific was weird. Method. That's what we're going to be looking at right now. There is no single route to answering a question that explains an observation. So yeah, scientific consensus is when you have a group of scientists and the scientific community actually attempting to answer something and all coming to a similar answer, if not the exact same answer. It's often that no consensus is ever going to be exactly 100%. Let's see, where did we leave off? There is no single route to answering a question or explaining an observation, but there is an aspect common to every approach. Each uses the knowledge based on experiments that it can be reproduced to verify the results. Meaning that if you try and come up with a hypothesis, if it cannot be recreated, it is basically to be discarded because it's unfalsifiable. That's the word we're looking for. You cannot make it false by definition. Some routes involve a hypothesis, a tentative explanation of observations that acts as a guide for gathering and checking information. A hypothesis is tested by experimentation, calculation, and or comparison with the experiments of others and then refined as needed. Meaning every time someone recreates it after having the experiment shown to them the first time, they can make little adjustments and make things work out to help explain the hypothesis itself. Some hypotheses are attempts to explain behavior that is summarized in laws. Now, this is not like the normal law that you find in the streets. These laws are basically unbreakable. That's their definition, what it means to be a scientific law. The laws of science summarize a vast number of experimental observations and describe or predict some facet of the natural world. If such a hypothesis turns out to be capable of explaining a large body of experimental data, it can reach the status of a theory. Now, theory, I want to go ahead on this one too, because theory, as it's used colloquially, is something a bit different in the scientific world. A theory in normal, everyday colloquial language can often be chalked up to a hypothesis. It's like, I have a theory. It's like, I have a theory that I'm going to walk outside and a big pile of cash is going to fall on my head. But yeah, that's not what evidence do I have to support that's going to happen. Now, a theory in science is like gravity. Gravity itself is a theory. We know basically how it works. I mean, there are many things we don't know. We know actually next to nothing about gravity, but not the point. We know that things go up and they fall down. That's the law. So to call that a theory as if it were a hypothesis is just like to say I'm going to fall off of a building and then I might hit the ground. No, theoretically, I'm going to hit the ground. So let's see. Scientific theories are well substantiated, comprehensive, testable explanations of particular aspects of nature. Theories are accepted because they provide satisfactory explanations, but they can be modified if new data becomes available, meaning that theories are not set in stone. Theory of evolution. We know it to work, we know how it works for the most part, but something could come along and change the theory a bit. The path of discovery that leads from question and observation to the law or hypothesis to a theory, combined with experimental verification of the hypothesis and any necessary modification of the theory, is called the scientific method. So here's the scientific method. Basically, we have an idea here. Something pops up, it piques our curiosity. Like, I wonder if this will work. I wonder if I pour a little bit of this water down the tube, what it will do. So I think the water may just sit still. I mean, the tube's open. The tube is open, so let's say we have a glass here. Well, let's do it this way. We have our glass. Now, we don't really know what's going to happen when we try this, do we? We have a little water in here. It's going to fall out. We know that. So, we have a little tube that's going to run, like that. test my art skills a little bit here. We have our tube. We think maybe the water will stop right there. Why would it stop right there? No, that's just where I feel like it's going to stop. So we make our prediction. The water goes down, and as we can see, the water goes, but it continues to go all the way around and out the bottom. Now, where do we go from here? We formed our hypothesis. We made a prediction. Further testing does not support the hypothesis. We actually tried to pour the thing, and we found that's what happens. The water does not, in fact, stop right there. In fact, we had no reason to ever think it did, but, you know, that was our hypothesis. So, perform an experiment, make more observations. We poured it a second time. We actually didn't have to pour it a second time. We poured it the first, and we saw it go all the way through. So it contributes to a body of knowledge. We now understand that the water, if poured and it is not obstructed in any way, will fly out the other end of whatever it's poured into. So long as it's pointing down, anyways, obviously. But that's part of the hypothesis. We learned that because we're pouring from here, that the water must go through the thing. And it becomes, observation becomes law, hypothesis becomes theory. So much additional testing yields constant observations. Because we will see, as many times as we pour it, over and over and over again, it will always fall down and always fall through, provided there is no obstruction. That's the scientific method in action. More or less right there. I don't like the way that was underlined. Well, I slid my entire tablet across the screen. But yeah, scientific method in action. Let's see. We'll call it there for this video, and we'll pick up next time. Alright guys, remember, always love one another, enjoy learning, and I love you guys. Mean it. Bye.